This recording is about mathematical relationships, and I want you to explore the different types of graphs that we're going to be using throughout this unit and for many units actually from now until the end of the school year. So the graph you're looking at now, one thing that I want you to notice is that, look, it goes through the origin down here at 0. And if you notice, if you look along the x-axis here and along the y-axis here, what do you notice? They are numbered pretty much the same here. We've got, a complete direct relationship, a straight line. It passes through the origin. If you look, it goes up proportionally, and any graph that you see like this that goes through the origin here and is a straight line is going to be a direct proportion. In other words, as the x value goes up, the y value goes up as well. So that one's pretty easy to spot. And here are some other examples of direct proportions. One thing I want you to notice here is that when I go from 2 to 4 on the x-axis, you can see what's happening. I have, times 2, that has doubled. And what's happening on the y-axis, if I come across here, when I go from 2 to 4, well, look, I've gone from 5 to 10. That indeed is also times 2. So a direct relationship is exactly that. If the x-axis doubles, the y-axis doubles. Let's check and see if the x-axis triples, if that's also the case. So if I go 2 times 3 is 6. If I go from 2 to 6, which is times 3, let's see what happens. I'm going to take 6 and I'm going to go all the way up here, find 6, and I'm going to go across to 15. And at 2, I started at 5. Well, indeed, 5 times 3 is 15. So this tripled as well. So direct relationships, that's exactly what happens. Whatever's happening along the x-axis, the same thing is going to happen along the y-axis mathematically. So this is an example of a direct relationship graph. It's just a random graph, and you can see if you were to extend this line backward, it would in fact go through the origin. And we'll be doing lots of labs that have direct relationships, and you'll get many chances to graph graphs that look just like that. The same thing is happening here as far as these variables increasing. Take a look as I go from 2 to 4. So if I go from 2 to 4 on the x-axis, what happens on the y-axis? I go from 2 to 4. So check. That is definitely a direct relationship. Whatever happened on the x is happening on the y. Now, what can get a little bit tricky is that a linear proportion can sometimes look like a direct proportion. It's the same thing. It's a straight line. You can see that the axes have numbers that are both increasing in value that look like they're moving along at about the same increments. But what you'll notice here is that this line does not indeed go through the origin. It goes through some other point. So as the x values are going up, the y values are also going up, but it does not go through the origin here. And you can look and see when the x value doubles, when I go from 2, which ends up at right about here, to 4, which ends up right about here, do these also double? So let's take a look at 2. We're right about here. That's supposed to be a dot. And at 4, we're right about here. And if we extend those over, at 2, we're like right in here somewhere, and at 4, we're like right in here somewhere. As I go from 2 to 4, I have doubled, so times 2. But what happened here? Take a look at that for yourself and see what you think. Did that double? It did increase, but did it exactly double? No, it doesn't look like it did. So that's the thing you want to look for when you're looking at a linear proportion, is that, yep, it is a straight line. Yes, as one variable goes up, the other variable goes up. But no, when we go from on the x-axis here, when we double it here, it does not double here. Here are some examples of linear relationships. Again, these are not direct, these are linear. So if we take a look at graph number 1 here, you can see we've got the husband's age versus the wife's age, and you've got all kinds of data here in the middle that they've collected, and indeed it is increasing here as the husband's age increases, the wife's age increases, and so this is definitely a linear relationship. This is not a direct relationship. It doesn't necessarily go through the origin. Over here, trace concentrations of benzene in a hydrocarbon. If you take a look, it is not going through the origin. Definitely a linear relationship. Things are happening here in a linear sort of fashion, but it is not a direct relationship where we have, a mathematical increase on this x-axis that matches the increase on the y-axis. So definitely as x goes up, y goes up, but it does not go through the origin. It is a nice straight line. Down here as well, we're looking at square footage versus price, the market price for a house. Same thing, straight line. It's a nice linear relationship. It does not go through the origin. So we know for sure that this is linear, but it is not direct. Over here as well, does not go through the origin. But you can see, again, it is definitely a linear relationship. But mathematically, you can see that as these values go up on the x-axis, how they are definitely increasing on the y-axis, but not by the same proportion. Another type of relationship is an inverse proportion. Now, inverse, you're typically going to see here a negative slope, so your line's going to be going down. In other words, as your x-axis numbers are going up, your y-axis numbers are going down. So it is inverse. Now, this is not the same as indirect, and I want to make sure that you're really paying attention to that, because indirect just means as one goes up, the other goes down. But this is a little bit more specific. It's exactly inverse. In other words, as x doubles, y decreases by half. As x triples, y decreases by a third. So you're literally taking the inverse of a number on these graphs. And you can go ahead and check that out for yourself. So if we look at 2 here and we go up to where 2 hits this axis and comes across, and 4, bring that up and have it come across, you can see that as this doubles, this goes down by half. Let's try another one. Let's go from, I don't know, maybe 5 to 10. As I go from 5, that's at about 2, and I go to 10, well, look, that's at about 1. So as I go from 5 to 10 over here, that doubled. So this is times 2, it doubled. And as I go from 2 to 1 over here, that number cut in half. So you can see it's literally the inverse, and you can just practice with that on this graph right now. Just kind of take a look, try a couple numbers, and see if you can see that relationship. This is an example of an inverse relationship where you can see that, let's just say as I go from 2 to 4 on the x-axis here. So I go from 2 to 4, so from here to here, you can go ahead and check it and see what you get. So on the x-axis, as I move from 2 to 4, I'm doubling. You go ahead and see what happens on the y-axis at the corresponding values there. It's got to be the worst y I've ever drawn. Let's try it again. On the y-axis here, what are the corresponding values? You go from one value down to another value. And I want to know what happened. Go ahead and try it. And just as a hint, it should be half. Okay, this is a squared proportion, and I want you to see if you can figure out why this is a squared relationship. And so probably the best thing you could do is maybe start at, I don't know, maybe 2, and take that across to the y-axis, and then it doubles as it goes to 4, and take that across. Or you could go, try from 3, take that across, and then 3 doubled is 6. Take that across, and see if you can figure out why we call this a squared relationship. Just pause the video. Okay, I'm going to go ahead and do this one. I'm going to take, the 3 across and the 6 across, like so. And as you notice, on the x-axis, when we moved from 3 to 6, that was taking 2 times, right? 3 times 2 is 6. So that was 2 times greater to go up. And as I went from 3 to 6 here on the x-axis this way, I moved from about 2.5 to about 10, and you can do the exact math, the lines on the graph there. But on the y-axis, I moved from about 2.5 up to about 10, which is 4 times, which, by the way, is 2 squared times bigger. So what I want you to notice is that whatever happens on the x-axis, if it doubles, on the y-axis you are going to get that squared moving up. So we can try tripling it. Let's take a different color here. If I go from 2 to 6, 2 to 6, then I get 3 times. I've tripled it. And then if I go from over here, 2 hits about, 1.5 up to about here. It's about 9 times. So we're at about 1, and we increase to about, it's actually a little bit more than 1, to a little bit more than 10. So that's 9 times. 9 times bigger. And you can go ahead and check the math there perfectly on that graph. But as I went 3 times bigger on the x-axis, I went 9 times bigger on the y-axis, which, by the way, 9, of course, is 3 squared. So that is why we call this a squared relationship, is because whatever's happening on the x-axis is mirrored on the y-axis by the square. Here's an example of a squared relationship. It's a velocity versus radius graph, and you can actually see the equation of the line up here. And anytime a graph includes an equation of the line, you can always take a look and see what is happening in that equation. And if you look closely here, you can see, in fact, we have an x squared. And so then you will know you've got a squared relationship there. And you can actually test this one pretty easily if you like. You can go ahead and check it out. As I move from half to 1, isn't that doubling? If I take 0.5 times 2, doesn't that give me 1? And same thing, if I move from 0.5, which is about, I don't know, you have to check exactly where that's hitting here, just slightly over 0.1, and 1 is at 0.4. So if that's doubled, this is going up 4 times. So as this side moves up 2 times, this side moves up 2 squared, or 4 times. You can see I go from about 0.1 to about 0.4. That's about 4 times bigger. So same thing, we're moving up as the square on this graph. The last graph that I want to show you here is an inverse square. And it's exactly what you would think. It's what we just did a moment ago, but inverse. So you can see when we move from 6 to 12, and I want you to go ahead and try it. Bring it up, see where it goes. Go ahead and pause the video and see if you can see that proportion. What you should see is that as you move from 6 to 12, you're moving from about 10 to about 2.5-ish as you go down. So as the x-axis is increasing from 6 to 12, it's doubling, the y-axis is decreasing by the square, by 2 squared, or by 4. In other words, if you take 10 from the y-axis there and divide it by 4, because it's decreased by a factor of 4, you get about 2.5, which is indeed where it ends. We move from 10 down to about 2.5 on that graph. So maybe try, 2 other places on that graph and see if you can come up with that same proportion. This is an example of the inverse square. And it has to do with the relative intensity of light as compared to the distance you are from the source. So we've been talking about light in the last unit, and what happens is if you've got something like a flashlight and you are shining that flashlight on something, and that light is propagating across and hitting a piece of paper or whatever. What this says is as you get further away from the source, so as your distance from the source is increasing, the intensity of the light is decreasing by the square. So as your flashlight gets farther and farther away from the paper, how bright that light is on the paper doesn't decrease in a direct way, it decreases in a squared way. The further you get away, it goes down by the square. So you can see that on the graph here, and they've put the proportions in there for you so you can see how that goes.